Today we're going to go over problem 4 from the 2024 University of Maryland High School Math Competition Part 2. So here's the problem. The problem is asking us to prove an inequality for positive integer n. Okay, so the first method that we're going to try is naturally induction. And by the way, I suggest that you take some time and work on this problem to appreciate the difficulty of this problem. Because when I made this problem and I proposed for our competition, I thought this would be an easier problem. But it turned out that only one student was able to solve this problem completely. Most of the students that tried induction, which seems to be a very natural approach to this problem. So what do we do for induction? We'll start with basis step. Basis step would be n equals 1, and naturally we would be able to prove that. So 1 over 2 is less than 1 over root 3, which is true because 2 is more than root 3. So now inductive step is we assume the inequality for n, and we want to prove it for n plus 1. So we assume that 1 times 3 times 2n minus 1 over 2 times 4 all the way to 2n is less than 1 over root 3n. Now we want to get to the next step, so we'll have to take the fraction and multiply that by 2n plus 1 over 2n plus 2. And we want to show this is less than 1 over root 3 parentheses n plus 1. So let's first write down this one as less than 1 over root 3n, and then keep the rest of it. And what we want to show is that this is less than or equal to 1 over root 3 times n plus 1. Now we don't know this inequality. We want to prove this one. If this inequality that I had a question mark on top, I put a question mark on top. If this inequality is valid, then the original inequality is going to be proved. So let's simplify this to see what we get. So we get 2n plus 1 over, we can factor root 3 and cancel root 3 from both sides. We can factor a 2 from the bottom, and we get 1 over root n plus 1. Now we can square both sides, so we get 2n plus 1 squared is less than 4 times n plus 1 squared over n plus 1. So I multiplied both sides by the denominator of the left, and I squared both sides. So this is going to be 4 times n plus 1. And if we expand this side, we are going to get 4n squared plus 4n plus 1 is less than 4n plus 4. And that obviously isn't valid because this is a quadratic, and the quadratic is not less than a linear. So what is the issue with this? Well, the issue is this inequality is strong enough that we can't really solve this one. So we're going to simplify root 3, and we are going to rewrite this inequality as 2n plus 1 over root n times 2 times n plus 1 less than 1 over root n plus 1. We are going to square both sides, so we get 2n plus 1 squared over n times 4 n plus 1 squared is less than 1 over n plus 1. So n plus 1 cancels, and we get 2n plus 1 squared is less than 4 times n plus 1. So this is the same as 4n squared plus 4n plus 1 is less than 4n squared plus 4n, which clearly this is not a valid inequality. So this method of induction does not really work for this problem. Now from here, what you can do sometimes is when the induction method fails, you start strengthening your inequality or whatever the inductive hypothesis is, in the hope that you can prove induction because you have a stronger inductive hypothesis. So here is now what we're going to do. We are going to strengthen the inequality, and we are going to prove that in fact 1 times 3 times 2n minus 1 over 2 times 4 all the way to 2n is less than or equal to 1 over root 3n plus 1. We are going to slightly make this one stronger. Let's see why this inequality is true. So we're going to use induction again. So basis step would be for n equals 1, which gives us 1 over 2 is less than or equal to 1 over root 3 times 1 plus 1, which is in fact 1 over root 4. This inequality is valid because both sides are 1/2. Inductive step can be done this time if we start with assuming 1 times 3 all the way to 2n minus 1 over 2 times 4 all the way to 2n is less than or equal to 1 over root 3n plus 1. Then we can multiply both sides by 2n plus 1 over 2n plus 2. So we have 2n and then we have 2n plus 2. And this would be less than 2n plus 1 on top. Then we have 2n plus 2 times root 3n plus 1. So this is what we know to be true. Now if I prove that this is less than or equal to 1 over root 3n plus 1, then I would be done. And again, I don't know this inequality. If this inequality is true, by the way, I also need a plus 1 here. If this inequality is valid, then I'm done. So let's see if that is in fact valid. So when is this inequality going to hold? And so I'm going to cross multiply and square both sides. So I get 2n plus 1 squared times 3n plus 4 is less than or equal to 2 times n plus 1 squared times 3n plus 1. Now, I'm going to leave the details out, but after you square this one and multiply it out, you end up getting that the inequality is in fact valid. So after you do all of the computation, you see that this inequality is valid. Therefore, the inequality is going to be proved by induction. And because we proved some stronger inequality, so this is going to be less than 1 over root 3n, so we are done with the proof of the inequality. Now I'm going to give you a couple of other proofs for this problem. This was the intended solution, the solution that I had in mind when I put this problem on the math competition. Now here is a second solution. So when you look at the inequality and you see that it fails the induction fails, you think that maybe the induction kind of backwards works. So what does that mean? It means if the inequality holds for n plus 1, then it holds for n. So let's see if we can prove this statement. Well, if the inequality holds for n plus 1, then we have 1, 3, 2n plus 1 over 2, 4, all the way to 2n plus 2 is less than 1 over root 3n plus 1. If this holds, I want to see if it also holds for n. So I'm going to do some sort of an induction, but kind of backwards. If you can do that and you can prove that this inequality holds for infinitely many n's, then you are done. So let's see. We're going to multiply both sides by 2n plus 2. We're going to create the case of n. So we're going to multiply by 2n plus 2 and divide by 2n plus 1. So we know this inequality. We are going to factor 2 on top. We're going to get 2n plus 1, root 3n plus 1. And we are going to simplify this to 2 root n plus 1 over 2n plus 1 times root 3. So if we can show that this is less than 1 over root 3n, then this backwards induction shows that if the inequality is true for n plus 1, then it would be for n. Then what we need to prove is that the inequality actually holds for infinitely many values of n. So let's clear the denominators and square both sides. So root 3 cancels. We get 4 times n plus 1 times n is less than or equal to 2n plus 1 squared. So this is the same as 4n squared plus 4n is less than or equal to 4n squared plus 4n plus 1. So this shows that in fact, if it is true for n plus 1, if the inequality is true for n plus 1, then it is also true for n. So if we show the inequality holds for infinitely many n's, then it would hold for every n. Then it would hold for every n. Why? Because you can kind of start from a large n that it works and then work backwards. And then everything below that, the inequality also holds. How do we show that it holds for large values of n? Let's look at the fraction that we have. We have 1, 3 to n minus 1 over 2, 4 all the way to 2n. And we want to show this is less than root 3n, 1 over root 3n. So we're going to multiply by 1 over root 3n, or I guess root 3n, but I'm going to get rid of the 3. So this is going to be equal to, we will turn this into factorials, and then we're going to use Stirling approximation. So we're going to multiply the numerator by 2, 4, all the way to 2n, so that we can turn this into factorial. And at the bottom, we get 2, 4, all the way to 2n, but all of that is going to be squared. And this is going to be, on top we have 2n factorial, we have a root n, and at the bottom we have n 2's, get 2 to the n times n factorial, all of that squared. So this is 2n factorial root n over 2 to the 2n n factorial squared. Now we have a Stirling approximation. So what is the Stirling approximation? It tells us that n factorial is approximately e to the negative n, n to the n times root pi n. So what does that mean? It means the limit of n factorial over this quantity e to the negative n, n to the n, root pi n, as n approaches infinity, is in fact equal to 1. How would that help? Well, we can say that if we take the limit of this quantity and apply this one for both n factorial and 2n factorial, apply this approximation, the limit is going to be some certain value, and hopefully that value is less than 1 over root 3. And if the value is less than 1 over root 3, then it would be less than 1 over root 3 for infinitely many values of n. So let's examine the quantity that we were given. So we have this quantity 2 to the 2n, n factorial squared. So Stirling approximation tells you this is the same as, or approximately the same as, we're going to replace 2n in here. We get e to the negative 2n, 2n to the 2n, root 2n, and then root n. At the bottom, we get 2 to the 2n, and then we get e to the negative n, n to the n, root pi n. I guess I had root pi times 2n, and then all of that squared. And approximation means the ratio, in this case, it means the ratio is 1. So I did all of that computation. Now let's simplify to see what we get. Well, we have an e to the negative 2n here, so this cancels conveniently. We have 2 to the 2n that it cancels here, and we have n to the 2n here also that it cancels. We have a root n here, a root n here that it cancels with that. So this is the same as root pi over pi, which means this is 1 over root pi. So what does that mean? It means the limit of the sequence that they gave us, 1, 3, all the way to 2n minus 1 divided by 2, 4 all the way to 2n. If you multiply that by root n as n approaches infinity, is going to be exactly 1 over root pi. So that limit is 1 over root pi, which is less than 1 over root 3. So if the limit is 1 over root pi, it means for infinitely many values of n, this quantity, so for n larger than some value, this quantity 1, 3, 2n minus 1 over 2, 4, 2n times root n is going to be less than 1 over root 3. And in fact, not just 1 over root 3, but 1 over anything that is less than root pi. And because this inequality holds for infinitely many values of n, it would hold for every value of n. So this is the second solution. Here is the third solution to this problem, which was another solution that I had in mind, but nobody really came up with this solution in the on the test. So let's look at the inequality that we were given. And one thing we could do is to square both sides to see what we get, just to get rid of this square root. That's kind of natural to do. We are going to get 1 squared, 3 squared, all the way to 2n minus 1 squared over 2 squared, 4 squared, all the way to 2n squared. It's less than 1 over 3n. Now here's the tricky part. If you look at the numerator, we can pair up these numbers. We get 1 times 3, we have 3 times 5, 5 times 7, all the way to 2n minus 3 times 2n minus 1, and we are left with a 2n minus 1. 2 squared, 4 squared, all the way to 2n squared. Now, if you look at the numerator, 1 times 3 is in fact 2 squared minus 1. 3 times 5, which is 15, is 4 squared minus 1. 5 times 7 is 6 squared minus 1. So all of these are squares minus 1. Because they are difference of squares, 2n minus 3 is 2n minus 2 minus 1, 2n minus 1 is 2n minus 2 plus 1. So that's the difference of squares, which means if you look at this fraction, every one of these fractions is going to be less than 1. So I'm going to write it down. So we get 2 squared minus 1 over 2 squared, and then 4 squared minus 1 over 4 squared, all the way to 2n minus 2 squared minus 1 over 2n minus 2 squared. And then we are left with 2n minus 1 over 4n squared, which is the last term at the bottom. Every one of these fractions is less than 1. So every one of these fractions is going to be less than 1, which means this whole thing is less than 2n minus 1 over 4n squared. And I need to show this is less than 1 over 3n. Unfortunately, this is roughly 2n over 2n squared, which is 1 over 2n, which is larger than 1 over 3n. So this doesn't quite work. Here's how we can fix this one. If we start computing the first few terms, then it gives us what we want. We want a factor of 2/3 to get to 1 over 3n. So here's what we're going to do. We are going to look at the first few terms. So 1 squared, 3 squared, 5 squared, 7 squared, 9 squared, and 11 divided by 2 squared, 4 squared, 6 squared, 8 squared, and 10 squared. And then we're going to pair up the rest of them. 11 times 13 over 12 squared. So this is less than 1 all the way to 2n minus 3 times 2n minus 1 over 2n minus 2 squared. And then we have 2n squared, and here we have 2n minus 1. Yes, we have 2n minus 1. Now, if you compute this quantity, so it's going to be a bit computational, but it's definitely possible to do manually. This is going to be less than 2/3. The rest of these are going to be less than 1. So we get 2n minus 1 over 4n squared. So this becomes 2n minus 1 over 6n at the bottom, 6n squared, which is less than 2n over 6n squared, which is 1 over 3n. That's exactly what we wanted. This only works after a point after for n equals 6 or above, and for n equals 1 through 5. So we have to check for n equals 1, 2, 3, 4, and 5. So manually we check these, and after that, this method does work. And that brings me to the end of this solution. I will see you in the next video.